welcome to another module in this massive open online course.
We are looking at convolutional codes, and we have looked at various forms of representing convolutional codes such as the generator matrix. And we have also looked at the D-transform domain representation of a convolutional code. We have looked at a feed forward that is a shift register representation, that is a shift register design or a shift register architecture for a convolutional code. Let us now look at one of the most important forms of representing a convolutional code, which is the state diagram to represent a convolutional code. And eventually from the state diagram we will build a trellis based representation of the convolutional code. So let us start with a state diagram, and this is similar to the finite state machine where you have states and transitions. So this is a state diagram representation. A state diagram representation of a convolutional code. Okay, obviously this is for a convolutional code, and again let us start by considering our code the same code that we have been considering so far, which is basically the code bit 0 at time instant j is xj plus xj minus 2. Needless to say, this is arithmetic in the binary field, correct? The plus and dot operations that we have seen before. C1j equals xj plus xj minus 1 plus xj minus 2. Okay, and now observe that at any time instant j, okay, so at any time instant j we need xj minus 2 and knowledge of xj minus 2 and xj minus 1. So what you can see here is at any time instant j, correct? To generate the code bits we need, correct, knowledge of xj minus 1 and xj minus 2, and these are the only symbols, the only information bits that we need. That is, given xj minus 1 and xj minus 2, right, at time instant j, we don't need the knowledge of any other past information bits. So at any time instant j, the information, that is the information bits xj minus 1 and xj minus 2 together of course with xj are needed, and only xj minus 1 and xj minus 2 from the past are needed to generate. We don't need, for instance, xj minus 3 or xj minus 4, etc. So the current state of this convolutional code, in some sense, if you were to think about it in that fashion, is captured by xj minus 1 and xj minus 2, because given xj minus 1 and xj minus 2, I can generate the code bits at this time instant, and of course I can keep generating. So the past evolution or the past history of this convolutional code, if I might say, is captured in these two, in this quantity xj minus 1 and xj minus 2. Knowing xj minus 1, xj minus 2, you can generate the code bits at this time instant, and more importantly, you don't need any other past right, any other past information bits, especially in the distant parts. Only you need xj minus 1 and xj minus 2. That is the important point to realize. Okay, and therefore given xj, what is important to realize is that here you can see that given xj minus 1, given xj minus 2, xj minus 2, one does not need any other past samples. Okay. So, what we are saying is this xj minus 1, xj minus 2 represents a state, xj minus 1, xj minus 2. This quantity, if you view this as a collection of 2 bits, represents the state of the encoder. This is an important notion, represents the, let me just write it clearly, represents the state of the encoder. This represents the state of the encoder. Okay, and now one can ask the question, how many such states are there? How many such states are there? For instance, let us look at xj minus 1, xj minus 2. Each xj minus 1, xj minus 2 can be either 0 or 1. So, xj minus 1 can be 0, xj minus 2 can be 0, or xj minus 1 is 0, xj minus 2 is 1, xj minus 1 is 1, xj minus 2 is 0, or finally both are 1. And you can see this is a simple application of the principle of total number of possibilities, and you can see the total number of possibilities, because each can be chosen in 2 ways. The total number of possibilities is 2 to the power of 2, that is equal to 4, and therefore total number of states So, the total number of states of this convolutional encoder, which as in a manner of speaking basically is represented, each state comprises of a particular value for xj for the past information bits xj minus 1, xj minus 2. So, the total number of such states in the convolutional encoder is 4. Okay, and the output code bits at the current time instant depend on the state plus the current information bit. So, knowing the current information bit, so knowledge of your current bit knowledge of the current bit and state, these together help us generate the code bits. Of course, at any time it's code bits for any time instant. So as to say, this convolutional code has a memory, because you need not only xj but xj minus 1 and xj minus 2, and this memory is captured by the state. Okay, memory represents an evolution of the system, and that evolution is basically captured by the state. And now the convolutional code can be represented using a state transition diagram, which shows the various states. And remember, the convolutional code transitions from one state to another state, right? For instance, at the current time instant xj minus 1, xj minus 2 are the past symbols. in j plus y time instant, at the next time instant j plus 1, xj and xj minus 1 represent the state. At j plus 2, xj plus 1 and xj represent the state. So the system evolves, correct, by transitioning from one state to another. At any given time instant, for any given input, it generates a set of code bits and transitions to a different state. Okay. So the convolutional code can be represented or can be thought of as a as a finite state transition machine, which is basically starts in a certain state, moves into a next state on arrival of an input bit, at the same time generates a code bit and moves into the next state, and this process keeps continuing. That is, this process of generating the code bits and transitioning from state to state keeps continuing as long as the input bits are arriving. Okay, so that is an important. So a convolutional code can be represented. So we wish to, so the point here is, if you look at a convolutional code, okay, this is captured by your state transition diagram, because convolutional code at every time instant is in a state, the encoder, and it transitions to a different or possibly the same state also, same state transitions to another state. There can be self transitions also, another state in the next time instant, of course, and generates code bits. Okay, generates also the code bits and generates code bits. So the state transition, so the generation or rather let us say the evolution of this encoder can be evolution of the encoder can be captured by state transitions. That is an important point that one has to realize, that is, it can be captured by the state transitions, okay, which are represented by the state transition diagram. So that is what we want to, and these state transitions, mechanism of state transitions, mechanism of transitioning from one state to another is represented by the state diagram. The mechanism so this mechanism of transitioning from one state to another is what is represented by the state transition diagram, which I am going to now illustrate. So we want to illustrate the state transition diagram for this convolutional code. We want to describe the state transition diagram for this convolutional code. And as we said, there are 4 states. So what we want to do is we want to capture this mechanism of convolutional code, that is encoder, the evolution of the encoder or generation of the code bits by this convolutional encoder through a state transition diagram. Okay. So, let us start. As we said, there are 4 states, correct. As we said in the beginning itself, there are 4 states. Okay. So, there is a state 0 0, correct, isn't it? There is a state, let me just write it, 0 0, there is a state 0 1, there is a state 1 0. We will just start by first writing all the states. There is a state 1 0 and there is a state 1 1. Just to make it clear, let us write them in different colors so that it becomes additionally clear. Okay, so there is a state 0 1, 0 0, there is a state 0 1, there is a state 1 0, there is a state 1 1. Now, in state 0 0, it means basically that xj minus 1 equals 0, xj minus 2 equals 0. Okay. Also, in state 1 0, this means that xj minus 1 is equal to 1, xj minus 2 is equal to 0. 1 1 means xj minus 1, xj minus 2 are both 1. Okay. So, that should be clear. Okay. Now, let us look at the transition. Now, let us say we get the information bit 1. Now, if the information bit 1 arrives, now let us think of it. Now, let us say xj equal to 1. We have j equal to, we have let us say j, time instant j, and state is equal to 0 0, which means xj minus 1 equals 0, xj minus 2 equals 0. Now, let us say xj is equal to 1. This is the bit, information bit at time, or this is the information bit at time j, information bit which is fed to the encoder. First information bit. Now, you can see if this is the information bit at time j plus 1, the state will be, well, state at time j plus 1, the state will be comprised of x, remember xj minus 1 will xj plus 1 minus 1, that is xj, which is equal to 1, and xj minus 1, correct, xj minus 1 here is 0. So, xj minus 1 will be 0. So, the state will be equal to 1 0. So, on arrival of 1, it transitions to the state 1 0, correct, because the 1 which is the information bit xj, which is xj, in the next time instant j plus 1, that will become xj minus 1, alright, and xj minus 1 will become xj minus 2. So, from 0 0 on arrival of 1, it transitions to 1 0. So, that is the whole point. So, it transitions to 1 0 on arrival of 1. Remember, this branch is represented by the input bit and the corresponding outputs. If you look at the corresponding outputs, what are the corresponding outputs? Well, let us look at the outputs. Outputs are, well, C naught j equals xj, that is 0, plus, or xj, that is 1, I am sorry, xj, that is 1, plus xj minus 2, that is 0, which is equal to 1, and C1 j, code bit 1 at time instant j, is xj plus xj minus 1, which is 0, plus xj minus 2, which is 0, which is equal to 1. We know the state, we know the current information input bit, and we know the state. We know the state means we know xj minus 1, xj minus 2. Therefore, we can generate the code bits, and we are seeing in this case that both the code bits are 1. So, the corresponding to input bit 1 we generate the code bits 1. Transitions to, so this is code bit 0 of j, this is code bit 1 of j. This is represented by this. So, on 1 it transitions to 1 0, and in state 0 0 on arrival of 1 it transitions to 1 0 and generates 1 1. So, the way to read this is from state 0 0 input bit equal to 1. So, it transitions to 1 0 and output equals, well, 1 comma 1. This is your C0 of j, this is your C1 of j. Okay, so that is the whole point. So, that is the point, and therefore, now similarly, now if you look at this, let us say we have x equal to 0. Now, you can see if xj equal to 0, next time instant at j plus 1 the state will be, well, xj minus 1, xj minus xj is 0, xj minus 1 is 0. So, it transition, it is self transition. Now, you see 0 self transition, it is 0, input bit 0, transitions only back to again 0, and the outputs are also, well, xj plus xj minus 2, 0 plus 0. So, C naught j is 0, xj plus xj minus 1 plus xj minus 2, 0 plus 0 plus 0. So, C1 j is also 0. So, at 0 transitions back to 0 and generates 0 comma 0. Now, let us come to the state 1 0. Okay, and now we have exhausted the possibilities for the state 0 0, because the inputs, remember 0 0, the inputs can either be 0 or 1. We have looked for 1, it transitions to 1 0, for 0 it remains in the state 0 0. So, we have exhausted the possibilities for state 0 0. Now, let us come to the state 0 1. 0 1 means xj minus 2, xj minus 1 equal to 0, or let us come to 1 0, xj minus 1 equal to 1, xj minus 2 equal to 0. Now, let us see what happens if a 1 arrives. Okay. Now, from 1 0, xj minus 1 equal to 1, xj minus 2 equal to 0. If a 1 arrives, the next state will be xj minus 1, which will be 1 comma 1. So, therefore, it transitions to 1 0, and the output will be, if you look at this, output will be in this state, well, in 1 0, let me just for the purpose of illustration at time j, right, xj equal to 1, state equal to 1 0, which implies xj minus 1 equal to 1, xj minus 2 equal to 0, transitions to, well, what does it transitions to? Transition to well, state 1 comma 1 at time j plus 1, and your C naught j equals, well, xj plus xj minus 2, xj equal to 1, xj minus 2 equal to 0. So, 1 plus 0 equals 1, C1 j equals xj plus xj minus 1 plus xj minus 2, which is basically xj is 1 plus xj minus 1 is 1 plus xj minus 2 is 0. So, binary field addition, this is 0. So, the output will be 1 comma 0. So, it transitions to 1 1, output will be 1 comma 0. Okay. So, basically in state 1 1 0, if the input bit is 1, it transitions to 1 1, output bits, code bits are 1 comma 0, that is C naught j is 1, output bits are 1 0, C naught j is 1, C1 j is 0. Now similarly, if you get the input 0, naturally it transitions from 1 0 to, because xj, if xj minus, so xj, so in state 1 0 xj minus 1 equal to 1, xj minus 2 equal to 0, if the input bit is 0, xj minus 1, so it transitions to 0 1, and you can check the outputs are 0 1, because the first bit is 0 plus 0, that is 0, C1j will be 0 plus 1 plus 0, that is 1. Now we have exhausted 1 0. Let us come to 1 1. In 1 1, if you get 1, it is obvious that you will transition back to 1 1, because xj is 1, xj minus 1 is 1, xj minus 2 is 1, so it will transition to 1 1. The output will be 1 plus xj minus 2, that is 1 0, 1 plus 1 plus 1, xj plus xj minus 1 plus xj minus 2, 1 plus 1 plus 1, 1 plus 1 is 0, 0 plus 1 is 1. In 1 1, if you get 0, input bit is 0, needless to say it transitions to 0 1, the output will be 0 plus 1 is 1, 0 plus 1 plus 1 is 0, so output will be 1 0. Finally coming to the state 0 1, in this if you get the input 1, naturally it will transition to 1 comma 0, because if the xj is 1, xj minus 1 is 0, it transitions to 1 comma 0. The output bits are 1 plus 1, that is 0, 1 plus 0 plus 1, that is also 1 plus 0 is 1, 1 plus 1 is 0, because the addition is on binary field. And finally from 0 1, if you get 0, xj is 0, xj minus 1 is 0, so it transitions to 0 0. The output bits are 0 plus 1, that is 1, and 0 plus 0 plus 1, that is also 1, so the generated outputs are 1 comma 1. Okay, and this is the state transition diagram for the convolutional code. And now we have considered all the states, exhausted all possible inputs, so we have generated the state transition diagram for this convolutional code, which we will see can be used to very conveniently generate the outputs of the particular code. Okay, so this is again the state transition diagram, which we have realized this. So here we have generated this, we have constructed the state transition diagram for this particular code. Okay. For instance, now let us look at a particular input sequence. Let us look at a particular input sequence and let us see what is the corresponding generated coded output sequence. So our input sequence is 1 0 1 1 0, the same sequence that we have considered previously, 0 0 1 0 1 1. So 1 0 1 1 0 0 1 0 1 1. So this is a time instant. So this is x, this is, I am going to write the time instant. First is 0 1 2 3 4 5 6 7 8 9. Now let us look at, represent the generated code. So I am going to draw now a table. It is convenient to think of this as a table, at least initially, correct? Okay, so let us look at time 0 1 2 3 4 5. Let us look at input. Let us look at our state, and let us look at our output code bits. Output code bits means C0 j, C1 of j. Now at time 0, the input is 1, correct? We will assume that the state is 0 0. That is, assume state 0 0 at time equal to 0, which means that we are saying that xj minus 1, that is x of minus 1 and x of minus 2 are 0. It is the same assumption that we have considered in the previous module, that is the previous inputs which we ignore, that is we have to start somewhere, correct, and the convolutional code depends on the previous input, so we consider them to be 0, which means we are now have an interpretation for that, which means that basically we are starting from the state 0 0, which is a reasonable assumption. Okay. So assume starting from the state assume that we are starting from the state 0 0. Now at time 0, remember time 0 state is 0 0, input is 1, so next state is 1 0 and output is 1 1, and that is important. So next state, you can see the next state is 1 0, output is 1 1. This is basically your next state. Remember, at every time, for instance time instant 0, you get state 0 0, input is 1, so next state is 1 0, correct, and the output is 1 1. Now we get input at time instant 1. At time instant 1, input is 0, state is 1 0. Now let us go back to our state diagram. 0 1 0, we are in state 1 0, input is 0, so it transitions to 0 1 and output is also 0 1. So the next state will be 0 1, output will also be 0 1. Now we are in 0 1, state is 0 1, at time instant 2, input bit is 1, at time instant 2, input bit is 1, we are in state 0 1, we are in state 0 1, input bit is 1, next state, correct, next state is 1 0 and output bits are 0 0, next state is 1 0 and output bits are 0 0. And in this fashion we can fill. So at time instant 3, input bit is 1, correct, time instant 3, input bit is 1, state is 1 0, next state is 1 1, output is 1 0. Okay, at time instant 4, input is 0, correct, time instant 4, input is 0, next state is 0 1 and output is 1 comma 1 0. Time instant 5, input is 0, next state is 0 0, output will be 1 comma 1. In state 0 1, we get input 0, correct, output next state is 0 0, output is 1 comma 1. Now let me just draw the rest of the table. So I will have and I will have at time instant 7 8 9. So at time instant 6, input bit is 1, next state is 1 0, output is 1 comma, output is 1 1. At time instant 7, input is 0, next state is 0 1, output is 0 1. At time instant 8, input is 1, output is 1 0, next state is 1 0, output is 0 0, and at time instant 9, finally input is 1, next state is 1 1 and output is 1 comma 0. And now if you look at this, so let me just quickly check it that I have not made any mistakes. You can again check it so as to verify that I have not indeed made any mistakes. Now you can see, therefore now you see this column corresponds to C0 and this column corresponds to C1. So let us write down C0 and C1. C0 equals 1 0 0 1 1 1 1 followed by 0 0 1, and C1 equals 1 1 0 0 0 1 1 1 0 0, and you should be able to check, correct. In fact, we had generated this by simply applying. If you look at this, for instance, this is for instance 1 0 0 followed by 1 1 1 1 0 0 1. If you can check it, go all the way back to our example where we consider an example for the generation of the convolutional code, example of output. For instance, here you will again see the same input sequence 1 0 0 1 1 0 0 1 and 0 1 1, and you can verify that the generated output code bits will be the you can see that the generated output code bits, for instance here you can see C0 is 100 1111 001, and therefore you can verify it. Okay, you can verify it and you should be able to check that we have got the same coded output bits. But this is much more simpler, correct, rather than doing the binary field operations at every time instant, considering xj plus xj minus 1 plus xj, or xj plus xj minus 2, or xj plus xj minus 1 plus xj minus 2. You simply, by looking at this, one can store the state transition diagram in the memory of a computer and quickly, very rapidly generate the coded bits by simply looking at the initial state, the input bit, transitioning to the next state, and at every time instant you simply need to store the current state, which greatly simplifies the memory requirement, correct. You only need to store xj minus 1 and xj minus 2. So and from xj you generate the coded output bits, transition to the next state, and generate, this way you generate the coded bits in a very rapid manner. Alright, and later we will see that based on the state transition diagram we will generate the trellis, and the trellis is very useful for decoding the convolutional code, which we will look at in subsequent module. Thank you very much.